Greetings to all again. Here we go with another class of Math 103. Today we're going to talk about the area formulas for specific figures that are polygons, but the simple ones. And we're going to discuss them mainly because I want to use the ideas from them to help show you a proof of the rule of Pythagoras that was done by a very famous American. But before we do that, let's get into this information today. Now, you see before you a typical rectangle, all right? This typical rectangle could be measured, and the length and the width of it, usually we refer to the bottom or the top of it as being its length, and the sides to the right and left being the width, could be measured and marked off. So what I'd like to show you next is we're going to discuss the area of this figure, and to do that I'm going to mark the figure off as you see here. Now for each of those marks, okay, those represent distances along those edges, okay? If you were to count the edges, or excuse me, if you were to count the distances that I have marked off, you'd find that I had marked off 12 units across the top and of course across the bottom, and then 6 units of height on the left and on the right, okay? Now you realize that if I mark those off in such a way, say these were centimeters, okay, I could completely fill this figure with squares that were 1 centimeter on a side. If I did that, it would look something like this. Now, if you notice, the area of this figure in centimeters would be, that would be square centimeters, would be found by counting up the number of squares of area I have, okay? If you were to count the number of squares that I have inside this figure, you'd find out that there are 72 of them. There are 12 across the bottom, and 6 going up the right-hand side, which is the height. So let's measure a few things or place a few labels on here. If we call the bottom of this the length, or L, if we call the distance going up the width, another name for the width could be the height of the figure, which I will denote by H, and of course across the top, instead of calling that the length, okay, I could conveniently take this L down here and move it upstairs. So if I took the length and moved it up here like so, okay, then I could take the distance down across the bottom and call it the base of the figure. So I'm going to do that now. I'm going to call this the base. The base and length are basically the same thing on a rectangle. The height or width are exactly the same thing on a rectangle as well, okay? Now, I know there are 72 squares here. If you decided to count them, you could find that. But notice I had said earlier there were 12 units of measured off in centimeters going across the bottom or the top. So the base of this is actually 12 centimeters long. The width or height is actually 6 centimeters long. Another way I could easily determine the area of this rectangle would be simply to multiply the length times the width, or the base times the height. And if I did that, I would get 6 times 12. Actually, I've got the 6 and 12 backwards, but does it make a difference which way I write it? Not really, because I'm going to multiply them. And you know, in multiplication, it is you can take the numbers and commute them to wherever you would like. You are still going to multiply them. So this says, basically, this says width times length. This says length times width. But at any rate, you can see that the formula that you've used all through school for finding the area of a rectangle can easily be shown here as the area equals its length times its width, or its width times its length. hopefully that has not given you any problems. The fact that I put width first, length second, it really makes no difference. So the first formula we have looked at and derived today is the area formula for a simple rectangle. So let's go on and let's take a look and write down up here the two possible formulas that I could use to determine the area of a rectangle. One would be A equals LW, or often it is used as A equals base times height. You simply take the number of units of a given kind that make up the width and make up the length, and you multiply them, or the base and height, whichever you would wish to refer to. So we know the formula for the area of a rectangle. It is one of these two, and we know it'll give us the number of squares of area that will fit inside that figure. Now, let's take a look at another very common figure that you were asked to learn in 6th and 7th grade to find the area of it. And if you look here, the next figure you see has opposite sides parallel to each other. And as you recall, it is referred to as a parallelogram. Well, how do you get the area of a parallelogram? Where did the formula for the area of a parallelogram come from? Well, the simplest way for me to show you that is to derive it by looking at the parallelogram and looking at the fact that I have a triangle and a dotted line over here that's vertical. What I would like to do first is I would like to take this triangle and I would like to place it, okay, in the figure. I'll turn it on and I'll move it over here. And you notice it fits right there on the end very nicely, okay? Now, if I were to chop off that triangle, okay? So in other words, if I were to take that triangle out of there like so, I'm going to bring it over here for a second. I'm going to bring down a blank rectangle and chop this off. What I'm going to do is take this vertical piece right here, if I can get it to turn on here. Okay, I'm going to bring it over here and put it right there. And then I'm going to take this particular triangle and stick it on here. Do you happen to notice anything? Well, what I have done is I have formed a rectangle by taking the triangular piece from the left and sticking it on the end of the figure on the right. Notice it's a rectangle. How do we get the area of a rectangle? Well, if we don't want to use LW here, but we can use the idea of base and height. For the base of this figure across here is exactly the same, all right, as the base of the original parallelogram I had, because I took that triangular piece off the other end. The height of the figure hasn't changed at all. So this dotted distance right here is referred to as its height. If I did base times height of this figure, I would get the area of this rectangle. But base times height would also give me the area of the parallelogram. If I take this figure here and I put it back on the other end, like so. Oh, can't see it because I've got this here. So let me take that out of there. If I put this back on here, the same parts make up the figure. So you can see that the area formula for determining the area of a parallelogram is simply A equals BH, where H is the height, the distance between the top and bottom parallel sides. Okay, so let me write that down here also. So for the area of a parallelogram, the formula is A equals BH. I could write it as HB, but I don't really need to, all right? Now that we've looked at that, we have two formulas so far we've discussed. We've discussed the area formula for the rectangle, LW or BH. Notice the formula is exactly the same for the parallelogram. We use a little bit different configuration for looking at the base and height, but it will also give us the area of the parallelogram. Now, let's go down here. We see another parallelogram, right? But along with this parallelogram, we see a couple other pieces over here, all right? Now, here's what I'm going to do. I'm going to take this piece right here, and I am going to take it into the parallelogram. Now, notice what I have done. I've split the parallelogram into two triangles. Well, I could use A equals BH. Let me write that down. A equals BH to get the area of the parallelogram, all right? However, I don't want the area of the parallelogram because what I'm trying to derive here is the area formula for a triangle. Well, you realize that if I cut a parallelogram in half, I do have a triangle that's formed, okay? The triangle that's formed has exactly the same base the parallelogram had. However, its height also would be the same, all right? However, I only want half of it. If I want just the area of the triangle over here, I only want half of it, right? So the formula that has been used by you for years for finding the area of a triangle is simply the area of a triangle is equal to 1/2 BH, okay? So the purpose of this triangle over here was just to show you that I'm not lying when I cut this thing in half. I wanted to show you that this fits right here, or if I flip it over, okay, it fits right here. Therefore, the formula you know is correct, and I'm not lying to you. If we want the area of a triangle, we can pretend that the triangle is a parallelogram that has the same base and height, okay, and then just take half of it. So 1/2 BH is the formula we use to represent the area or define the area of any triangle. All right, so now we have 3 formulas done. Let's take a look at this sweetheart right here. If you recall, let me extend this page a little bit, all right? And if you recall, this figure is called a trapezoid. In a trapezoid, you have a height, okay? It would be that dotted distance right down here. Oh, excuse me a minute here. Let me see if I can draw that down there. No, I can't right now. So let me just go back up here and steal the height that I have up here that used to be over here. You move this. Don't think I'm going to be able to move it there. I'm going to bring this down to this figure way down here. Okay. And I'm going to try to attempt to put the height right there. So there's the height of the figure, okay? It's the distance between the two parallel sides, all right? The non-parallel sides make up the other 2 sides of the trapezoid, okay? Now, I want you to watch this, okay? If I take this trapezoid right here, okay, and I'm looking to get its area formula, okay? What I'm going to do is I'm going to take it and I'm going to clone it. And when I clone it, I make one exactly like it. Okay, there it is. I'm going to bring it out here like this so you can tell that these 2 trapezoids are exactly identical. If I flip this trapezoid over like so, okay, and I take it over next to the trapezoid I already have, notice I have a huge figure. What is that huge figure? Well, if you take a look at it carefully, doesn't it look like a parallelogram? It is, isn't it? It is a parallelogram. Now, I want you to look at something here. If I take this piece, or this trapezoid piece, and just move it over here a little bit out of the way, I realize this is the height of the trapezoid, right? Right here, okay? Notice it has a base down here, but notice over here there's a base to this trapezoid, but it's upside down. So that's the reason why in the trapezoid formula you used your whole life, you had to do 2 bases in a trapezoid, the top base and the bottom base, when you figured its area. So let me erase this out of the way first here. Okay, I'm going to call this base number 1. Well, maybe I better try that again. I'm going to call this base number 1. And by the way, where would base number 1 be on the figure on the right? Well, wouldn't it be up here? Because I flipped it over, right? Okay, where is base number 2? Well, I'm going to call this base 2. Where would base 2 be on the figure on the right? Well, it would be on the bottom, wouldn't it? Now I'm going to put these two back together again to form the parallelogram. Now, how would I get the area of this huge parallelogram? Well, let's see. All I would have to do is go area, excuse me a minute here, area of the figure has to be equal to its base multiplied by its height. I'm going to write those words out. Base times height. Now, the height is still h in this diagram, right? But the base is made up of two pieces, B1 and B2. So I'm going to write those down. And how would I get their length? Well, I'd have to add them together, right? So I'm going to put that in parentheses because I have to add them together. So if I took base 1 plus base 2, added them together, and multiplied them times the height of the figure, I would have the area of this huge parallelogram. But wait a minute. I don't want the area of the parallelogram. I only want the area of the trapezoid. But I have two identical trapezoids here, right? So all I have to do is take half of the area of the entire figure's parallelogram, and that will give me the area of the trapezoid. So in other words, if I take this figure here and move it away, and I put a 1/2 out here in front of this, that's the area formula I use to get the area of a trapezoid. Now, we don't usually write it that way. You probably remember this from middle school and high school. The way we actually usually write it is how? Well, we usually put the h before the B1 and B2. So the area formula we use to determine the area of any trapezoid is area equals the height, okay, 1/2 put in front of that, and then I didn't do that very well, so let me start over again there. So the area is equal to, let me try again, let me move this up just a little bit. The area is equal to 1/2 the height of the figure, okay, and then we add the sum of the two bases, the top and the bottom, and if we do that, we will have the area of just the one trapezoid, not the whole figure. Pretty simple, right? Okay, so let's review what we've talked about, okay? Let's review what we've talked about. Okay, the area formulas that we have come up with, all right? Let me see if I can get my picture out of the way here. Okay, the area formulas we have come up with are, for the triangle, it is 1/2 BH. So let's write that down. A equals 1/2 BH. Here's the base. Here's the height down from the highest point of the triangle, like so. So this would be the height. Wait a minute. On the orange triangle to the right, where is the height on that figure? Well, as it turns out, the height on this figure is over here. It happens to be perpendicular to the base because it is a right angle right there. So that is a right triangle. So to get the area of a right triangle, I still use 1/2 BH, and I use the two legs of the right triangle to determine the answer. Okay? So there is the formula once again, 1/2 BH. All right? If we go over here to this crazy yellow trapezoid that you see here, okay, the trapezoid's area formula will be like we discussed a few minutes ago. Here's the height. Here are the bases. Base 1 can be the bottom. Base 2 can be the top. All right? And of course, the formula would be A equals 1/2 H multiplied times B1 plus B2. And the white-centered figure here that you see on the right is also a trapezoid. It's a little different trapezoid, but notice this one side is perpendicular to the base. This is still the height, okay? This would still be B1, this would be B2, and the area for it would also still remain 1/2 its height multiplied by the sum of the bases. Okay, now I have supplied you with a drawing of this sheet, okay, that I have given you, that I emailed you. And what I would like you to do is take a few moments, please, and when we do this next sheet, do the sample problems that we're going to do, okay? You can write down these formulas on the sheet that I provided for you, okay? All right? And when we go to this next sheet to do these problems, I would like you, please, to refer to the sheets that I have sent you, okay? Find those diagrams, and we'll do those together, okay? So this is the end of the first video we're going to do. When we come back on, we are going to be looking at these areas and practicing them, okay? All right, I'll see you in a few. All right, take care.